All right, calculus, here we go with slope field and Diffie nodes. So differential equations, best known by me as Diffie. So the first section is tangent lines to differential equations. Well, we know what tangent lines are. They're lines that go through one point on a curve. So a differential equation. Differential equation seems like a brand new word. It may be something we don't know yet, but we do. It's just, so looking at this example, the quantity of a substance can be modeled by the function a of t, the amount that satisfies the differential equation d of a dA dt. So this is the rate of a with respect to time. 1 point on this function is a of 2 equals 160. So that's a point, 2, 160. Based on this model, use a linear approximation to the graph of a at t equals 2. A linear approximation is an equation of a tangent line. Approximating linear, so we're using the equation of a line at t equals 2. To estimate the quantity of the substance, again, at to estimate the quantity of the substance at t equals 2.1. So we're going to find the equation of the tangent line at t equals 2 and use it to approximate t equals 2.1. We can do this, but it's only going to be accurate if we stay close to 2. So at time t equals 2, we have the point 2, 160. This was given to us when they told us a of 2 equals 160. So to write the equation of a tangent line, we need the point slope formula. So we have the point. Now the slope we need at this point, 2, 160. So if we sub 2, 160 into the equation for dA dt, okay, dA dt is equal to negative 1 over 20 times a. Well, a is the y value, because we have a of t given to us up here. So t is the x value, a is the y value. So we're going to replace a with our y value, 160, and we get negative 8. So we know the slope of the tangent line is negative 8. dA dt is this rate, which is the slope at the point is negative 8. We know the point, so if we sub them into the point slope equation, y minus y equals m times x minus x, and we add 160 to the other side, then we have the equation of the tangent line at x equals 2. Again, this is only accurate if we stay near 2. This would not be accurate if we tried to approximate a of 3 or a of 4. We have to stay close to 2 for it to be accurate. So we're now going to use this equation of the tangent line at 2 to approximate 2.1. So a of 2.1 is approximately, same equation, replace t with 2.1, and we get approximately 159.2. This is the y value, and the x value is 2.1. So we just use the equation of the tangent line at 2 to approximate the value 2.1. Notice how the y values are close. We went from 160 to 159.9. It only changed by a small amount. That is should almost always be true. You can use that as a way to check yourself that your y value stayed close as you change your x value a small amount. Okay, example 2. Consider the differential equation dy dx equals y cubed over x with a particular solution y equals f of x, having an initial condition y of 1 equals 2. So we have the point 1, 2. Use the equation of the line tangent to the graph of f at this point 1, 2 in order to approximate the value of f of 1.1. So we need to find the equation of the tangent line. We need the slope. The slope we will find by subbing the point into the derivative. Well, we already have the derivative. That's what the differential equation is. So we sub the point into the derivative. So y cubed, 2 cubed is 8, divided by x. X is 1. 8 over 1 is 8. So we have a slope of 8 at the point 1, 2. Write the equation of the tangent line, y minus y equals m times x minus x. Add the 2 over. And now we're going to use this equation of the tangent line at x equals 1.1 to approximate, use the equation of the tangent line at x equals 1 to approximate x equals 1.1. So we're going to sub 1.1 into the equation to approximate the y value. Algebra, we get 2.8, so we know the point 1.1, comma 2.8 is a point on this function, and we started with 1, 2. We stayed close to our x's and y's, stayed close to the same value. Slope fields. Okay. Slope fields are kind of fun. They're just the slope at every point in the coordinate plane. So it's just a bunch of slopes. So to select the differential equation, the equation that represents the derivative that matches the given slope field, remember differential equation, is to notice the slopes that are both vertical and horizontal, and pick those points out. So here, all along the x-axis, we have vertical slopes. Well, if we have vertical lines, vertical tangent lines, meaning the slope is undefined, and the slope is only ever undefined if we have a number over 0. So this is where y equals 0. So this will only happen when y equals 0 in the denominator of a fraction. And only knowing that eliminates all others. So only checking the vertical tangent lines in this case led us to the solution. Now we could check others. If that didn't eliminate all others, I would check the horizontal lines, which occur when x equals 0. Well, horizontal lines are when the slope equals 0, and this happens when we have 0 over a number. So x equals 0 will make the whole slope equal 0. Knowing that, the first one would be true, second one would not, the third one would be true. So there we would narrow it down to the 2. We could also, if you look here, look overall, the slopes are almost all positive, and they're perfectly positive along the diagonal with the slope of 1, like over 1 up 1, that point has a slope of 1. So if I sub in the point 1, 1, I want to get the slope dy dx to equal 1. Well, let's see where that would happen. That would not happen with the first one. It would happen with the second one. And what happened with the third one? Okay, so I'm back. I just crashed for a minute. So I was talking about how at the 0.11 and 223344 we get a slope of 1. So that was also true at number 3. Anyway, this one's correct. We know that. We proved it many times now. So a slope field is just the tangent line at each point. So it's the slope at each point. So we sub in the point, and what we get out is the slope. Looking at example 2 for slope field. So when you do this on Delta Math, I only assigned 1, not many. So it says create the slope field at the given points for the differential equation. Y plus 1 over x plus 1, change the slope using the small pink circles at the end of each line segment. So we can move and change the slopes at each point. So, okay, so when you do this section, you're going to sub in each point and then estimate the slope by moving the line to match that slope. So here we have the point -1, 0 subbed in. We can see the slope at -1, 0 is equal to 0, which is why the line is horizontal. So same thing at -2, 0. The slope is calculated to be 0, so it's a horizontal line. At 0, -1, the slope is undefined. We have a number over 0, so we have vertical lines along the y-axis. When we sub -1, -1 in, we get a slope of -1. When we sub -2, -1 in, we get a slope of -1/4, so this will flatten it a lot more. We sub in -2, -2, we've got a slope of -1. Parallel the slope at -1, -1, and subbing in -1, -2, we get a slope of -4, so it's more steep. So you're going to estimate those slopes, and again, you only have to do one of these on Delta Math. Okay, solving differential equations. Given the differential equation, so we're given an equation, which is a rate, so we're given a derivative. Find the particular solution of y equals f of x with the initial condition f of 2 equals -6. So we're given the derivative and 1 point. So dy dx is equal to x minus 6 over y. So if we separate the variables, meaning the y's on one side with dy, and the x's on the other side with dx, so essentially cross multiply, because we have a fraction equals a fraction, multiply the y over, multiply the dx over, then we integrate both sides, find the antiderivative of both sides, the left side with respect to y, and the right side with respect to x. Now, we would have a plus c here on this side as well, but you can combine the two constants. You don't need more than one constant when you have a constant. You can subtract this constant, and then you still have a constant. So it's just one constant written. If you want to write both, go for it. Plug in the initial condition. So we sub the initial condition in to find c. The ultimate goal is to find c. So that we can sub it back into the equation, and now we have all of our unknowns. So we plug C in and then solve for y. Now, since we have y squared, we must consider whether we need the positive square root or the negative square root. Since f of 2 equals negative 6, the only way to make a negative y value is to use the negative square root. So, from here, if we take the square root of both sides, then y equals the positive square root of x squared minus 12x plus 56 and negative square root of x squared minus 12x plus 56. Okay, so to figure out which one is correct, you can sub in the initial point that we've had, 2 comma negative 6. It must satisfy 2 comma negative 6. So if we sub in 2, we need to get out negative 6. That's only going to happen if we sub it into the negative piece, or you can try both pieces and you calculate it. Here, the final answer is y equals the negative square root of this function. So, to recap, we separated the variables of the differential equation, integrated both sides, used the initial condition, which is the point, to find c, plug c back in to this equation, right, where c first popped up is where you see sub c back into, and solve for y. All right, one more example. Given the differential equation dy dx equals x squared over 2y, find the particular solution with initial condition negative 3, negative 1. So we separate the variables by cross multiplying, integrate both sides, add 1 and divide, use the initial condition, the point, x equals negative 3, y equals negative 1, to sub into this equation to solve for c, plug c back in, and now solve for y. So if we solve for y, we're going to get y equals the square root of 1/3 x cubed plus 10, and y to equal negative the square root of 1/3 x cubed plus 10. Now, the initial point will tell you which one is correct. We need f of negative 3 to equal negative 1. So if I sub in negative 3, for x, I get 1/3 times negative 27 plus 10, so I have negative square root, negative 27 divided by 3 is negative 9 plus 10, so negative times the square root of 1, the square root of 1 is 1, so negative times 1 is negative 1. That satisfies the initial point, negative 3, negative 1. You check the other equation, you get out positive 1. Positive 1 doesn't satisfy the initial point. Diffie Q's and slope fields.